Hello, welcome to this lesson of our study of PD. Okay, so in this lesson we'll look at how to solve the heat equation using what we call the separation of separation of variable method. Okay, so let me take that point again. I said we're going to use a method called separation of variables method. Okay, so that is what you're going to use to solve this linear heat equation. Okay, so remember here is UT. Okay, the first one is UT. That's the heat equation in one variable. So the heat equation in this form, okay, subjected to these conditions. These are initial conditions plus boundary conditions plus an initial condition. The reason why I'm saying this boundary condition is you could see that the x is defined at 0 to L. That's the boundary, and then the function is also, or the functional value at those boundaries are given. I mean, u of 0 t, that means x equals 0, that point is 0, and u of lt is equal to 0. Okay, and that we have this as initial condition, u of x comma 0 to be that. Okay, now to solve this, we're going to use what we call the separation of variable. And the separation of variable is saying that we assume that the solution to this heat equation is this. Okay, the solution is a function of the product of two functions, where one of them is solely a function of x and the other is only a function of t. Okay, so we call that the function of x to be capital X of t and that of t to be capital T of t. Okay, so we can write, you are assuming that we can write u of xt to be capital X of x. So in other words, let's write it like this: to be equal to capital X then t. We know that these are functions of x and t, so this is a function of x and this is a function of t only. Okay, then it means that ut, using this u, will be differentiating the whole of this with respect to t. But then remember, x is a function of x, so it will behave as a constant. Okay, so we'll have x then t prime, or the small t, but let's call that t prime. And ux will be, let me first start with the ux. It will be x prime t, because t is a function of only time, and that it will behave as constant. So we'll differentiate the x rather, which is a function of x, and this will implies that uxx will be equal to, in differentiating this two times. So we have that. This implies that when you go to the heat equation, which we have this one, ut equals k uxx, will then give us something like this. Ut is xt prime, okay, and then uss is x prime prime then t. Okay, so this is what we have. Now let's write it again. Xt prime equals k x prime prime t. Okay, let's try to divide through by k. Okay, and we'll have something like st prime all over k is equal to x prime prime t. Now let's again divide through by t, and we'll have xt prime over kt is equal to x prime prime. Now let's go ahead and also divide through by x. Okay, so in other words, you are just trying to separate the variables, put all the t variables in one place or at one side of the equation, and put all the x variables. So if you continue and take this equation and divide through by x, or multiply each side by 1 over x, we'll have this x prime prime over x here. Now we are saying that t is a function of only time. Okay, let me rewrite this again as something like 1 over k times t prime over t equals x prime prime over x. Now know that since t and x are both functions of independent variables, okay, so t is a function of time. You said t is a function of time. It's not tau, sorry, it's actually t. we have t of t, and then we have x of small x. This means that if t prime, we have t prime over t is a function of time, so t prime of t is actually again another function of time. Okay, do you understand what I'm trying to say? You have a function of time, you differentiate it, so you get another function of time. You divide it by the same function and you get another function of time again. Also, with the x prime over x, that one too is a function of x. So everything here will be a function of x like this. And this side, if you do it, will be a function of t like that. Okay. So, but you are saying that they are independent. The variables are independent. But we are trying to say that this side should be equal to this side. We have one function being equal to another function. Okay. Which their variables are not the same. This means that they are actually constant functions. Okay, this t prime over t equals s prime over x will only happen when the ratio between any one of them is a constant. Let's call that one lambda. Okay, if this happens, then this is true, so we call this constant a lambda. If that is the case, then we can equate either one of them to the lambda. Okay, so we can say 1 over k t prime over t is equal to lambda. And we also have s prime over x is equal to lambda. If this is true, then our equation that we just said, this one holds. Okay, and this one too will hold because they are both equal to lambda, hence they are the same. Okay, if that is the case, then let's pick the first one, the first equation with a t prime, and solve. Okay, so remember that t prime is actually equal to d of capital T d small t. Remember this. Okay, and also with this equation, the one with the t prime, we can write it as t prime over t, actually multiplying both sides by k, we'll get k lambda. Okay, this will show that we have 1 over t times t prime equals k lambda. I'm trying to separate this and solve it for you systematically. Then you have 1 over t, then you said t prime is d capital T d small t, and this is equal to k lambda. So you have 1 over t d capital T equals k lambda d small t. We just pre-multiply each side by dt, and this is what you have. Now let's try to solve this, because this becomes a very simple ODE, a first order ODE, which has been separated already. So we just integrate both sides with their respective variables, and then we got our solution. Okay, so we have something like 1 over t d capital T equals k lambda d of small t. Okay, I think that is what we have, d of small t. So if you integrate this side and also integrate this side, here we are integrating with respect to capital T, here we are integrating with respect to small t. That's why I said they are separable variables. We've been able to separate them. So all that you do is integrate 1 over capital T with respect to capital T, and that will give you ln of capital T, and this is equal to k lambda then small t, because k and lambda are both constant, plus a constant, let's say c. So if I want capital T, ln is the logarithm to the base e, right? So let me write that this is the same as logarithm of t to the base e, and this is equal to, let me erase this and write it all for you. This logarithm of capital T to the base e, and this is equal to k lambda t plus c. Now to do this, we just let the exponent raise up to this side. Okay, and the logarithm will go. So we have t equals e to the k lambda t plus c. This is the same as e to the c dot e to the k lambda t. And e to the c, we can call this a constant, let's say a. So actually our capital T is equal to a constant a, e to the power lambda, or k lambda t. K lambda t. This is our function t, capital T. So T has been able to found. Now let's go ahead and solve for our x. Then we multiply them and we'll have our solution. Okay. Now we have the other equation was x prime over x to be equal to lambda. Now let's multiply both sides by x and c. This will imply that we will have x prime equals lambda x, and this will show that we have x prime minus lambda x equals 0. Now this looks like a second order ODE, very simple to solve. Okay, and that if I say that x of s, okay, should be equal to e to the power rx, then we have to differentiate this 2 times because we have s prime here. That means s prime will be equal to r squared e to the power rx. Now when you differentiate this for the first time, you get r times e to the power rs. Second time will be r times r e to the power rs, and that will be r squared. Okay. Alright, so with this, we just put these back in our equation. Now we have s prime minus lambda a. So s prime is now this, so I have to just put that in. I've already solved such a question in my eigenvalues or eigenfunctions, but I just want to go through with you, should in case maybe you didn't watch that. Okay, equal to 0. Then r squared, okay, minus lambda e to the power rx equals 0. Now e to the power r is a function. Okay, so it can be 0. We have product of this and this equals 0. It means either one of them will be 0. But then note that e to the power rx will never be 0. If it is 0, then we have a trivial solution. That's not what we want. Okay, so it means r squared minus lambda is actually equal to 0. This will show that r squared is equal to lambda, and that r will be r12, that is, we have a square root, so it's plus or minus square root of lambda. Now this is what we've gotten, right? So to find a solution, to solve for this, actually we have to consider cases. Okay, so the first case is to consider when lambda is greater than 0, what will happen. So case 1, we start with, let's say case A, lambda greater than 0. When lambda is greater than 0, then it means square root of this side will be r12 will be real numbers. So we'll have a general solution to be capital X of x equals e to the power square root of lambda, that's the first one, x plus, sorry, constant a, then a constant b, e to the power minus square root of lambda x. We have plus or minus there, so, and we said that this can be written as, when you have plus or minus something, it can be written as a cosh the square root of that thing plus b sinh, okay, the square root of lambda x. Now before we come here and continue, let me say something before. Okay, remember that we are saying that with the boundary conditions, we are saying u of s comma 0, sorry, with the boundary conditions, the first boundary condition, u of 0 comma t is equal to 0, and u of l comma t is also equal to 0. But we said something like u of xt should be equal to x of s times t of what? T. This shows that u of 0 comma t will be equal to x of 0 times t of t, and we are saying this should be equal to 0, and u of l comma t should also be equal to s of l t of t, okay, equals 0. Now let's go ahead and check our t, the t function. We said that our t, we solved t and we had t, the t to be equal to this, t of t is equal to an exponential function. And what values did we define for t? If you look at this, t is 0 is less than t, meaning t is actually, if I interchange them, t is actually greater than 0 from this. Okay, if t is greater than 0, if t is greater than 0, then it means t can never be 0. It should be positive numbers. Okay, sorry. Yes, this is what we have. It should be positive numbers, meaning that the t function will never be equal to 0. This one, because you're saying that t here is greater than 0. So for every value you put here, you don't have 0. This means the part that we have, the product of these two is giving me 0. We are saying that t of t will never be 0. The product of this is also giving me 0. But t of t will also not be equal to 0, meaning x of 0 should actually be equal to 0 for this one to be true. Because when f of 0 is equal to 0, then their product will be 0. And also s of l should also be equal to 0, so that this one too will be true. So we'll use these two conditions to solve, okay? Now, when we come here, x of 0 is equal to a cos 0, which is 1. So a plus b sin 0, which is 0. And this we are saying is equal to 0. This will show that a is actually equal to 0. And that our function x is equal to a is 0. So we have b sin square root of lambda x. And you're saying that x of l should also be equal to 0. So I'll put it here. I have 0 equals, or let me solve that one first. B sin L square root of lambda should be equal to 0. And now the sin function is 0 only when the argument here is 0. Okay, so sin of 0 is 0. But for sine, we have other values that can make it 0. But then we are talking about sin here. So this is 0 only when the argument here is 0. Meaning that if you pick this side, okay, lambda, we are saying is greater than 0. So it means lambda will never be 0. And we know L is also not 0. Therefore, the sin aspect will never be equal to 0 because the argument inside will never be 0. But we are saying that b times that should give us 0. Meaning our b should be equal to 0. Hence, our x is giving us b, which is 0 times that will give us 0. Which is a trivial solution. So s of x is actually 0. And we don't want this. We don't want a trivial solution. So now you go to the second case, which is the b part. Lambda equals 0. Now if lambda is equal to 0, then our x of s will then be equal to e to the power 0 plus bx is a repeated root. The lambda is actually equal to 0. So when it's equal to 0, you come here and you realize that you get r12 to be equal to 0 because square root of 0 is 0, and that means we have repeated root. And this is how you write this is how you write a repeated root solution, okay? E to the power 0, and this will give us s of x, that is for the second case, equals a plus bx. Now with this, you are saying x of 0 is equal to 0, which implies that a plus 0, because x will be 0 here, should be equal to 0, and a will be equal to 0. So with the second case, we have s of x, a is 0, then it means s of x is equal to bx. Again, x of l is equal to b times l, and this is equal to 0. That is from the condition. So bl is equal to 0 implies that b is equal to 0. That one too is giving us what? The trivial solution. So you know where we are getting to. The only case that will give us non-trivial solution is the case 3, where lambda will be less than 0. If lambda is less than 0, then the square root of lambda will be a square root of a negative number, because lambda is already less than 0. That is from here. So we'll have negative roots, complex roots. Square root of negative numbers will give us complex roots, meaning our x of s will be equal to, when you have complex roots, you write it in terms of cos and sine. A cos square root of lambda x, then plus b sine square root of lambda x. And now with the first condition, x of 0 equals 0, we implies that a, which is times cos 0 is 1, plus b times sine 0, which is 0, should give you 0, and that you have a is equal to 0. Now with the third condition, it means our x of s will reduce to b sine square root of lambda x. Okay, because a is 0. But then x of L is also equal to 0, which implies that we have 0 or b sine of square root of lambda times L. So L square root of lambda should be equal to 0. Now we have two cases. You see that this is 0 and this is not 0, or when both are 0. When both are 0, you don't want that because we'll get a trivial solution. When b is also 0, we'll get a trivial solution. But let's consider, is there any case lambda here is less than 0 though, but is there any case that the sign will be 0 apart from, we know that this is lambda, this is lambda, okay. We know that sign of 0 is 0, yes, but are there other values that their sign will give you 0? Let me clean here. Are there other values that their sign will give you 0? Yes, it's true. There are other values, so we should consider those values as well, because lambda is actually less than 0. So you consider other values that will make this argument 0. Okay, when b is 0, like I said, we have a trivial solution. You don't want that. So we want to set square root of sine of L square root of lambda to be equal to 0. And there can be cases where here is not 0, but then the sign of it will be 0. Example is sine of 2 pi is 0, but then the argument is not 0. So here we can get other values as well. So let's check that one. The reason why we didn't check for the signs is that for signs it's only 0 at x equals 0, or at when the argument is 0. But then we had already defined that lambda was greater than 0, and that means there was no way that part was going to go to 0. That's why we didn't do that one. Okay, now let's consider this. Like I said, we find sine inverse of both sides, and then you have L square root of lambda, and sine inverse of this will give you n pi. It means you should look for the angles that their sine will give you 0, and it's n pi, where n is starting from 0. But then when n starts from 0, we don't want that because we'll get lambda to be equal to 0, and that will give you a trivial solution. So we should start from n equals 1, 2, and the rest. Okay, now with this particular one, let's try to find lambda. Now you know square root of lambda here will be equal to n pi over L. This implies that our lambda will be equal to, or lambda n, because here there will be many, n pi over L all squared. Okay, that is what we have now. Now it means un of x, or maybe x of x. Okay, let me add that capital X of s is now equal to, now for all the cases we had trivial solution. It was only this case that we had a solution like this. X of x equals b sine of square root of lambda, and square root of lambda is given by this. Okay, then x, and that was the solution for the x part. Okay, so it's b n. The reason why I'm writing bn is because realize that the solution will have plenty or different solutions. Sine of n pi, because of the n here, over lx. Okay, this is what you have, and we said that t of t will then be equal to, what was t of t? E to the power, or a e to the power k lambda n t. Now the reason why I'm writing lambda n is because the lambda we found here is actually lambda n, not just lambda. Then this is a e to the power k, and lambda n is giving us n pi over L squared t. Okay, so we keep this. Now let's go to the final solution. We are saying that u of xt is equal to, this is what we said. Okay, this should be given by x times t, and then we found our x. Okay, so we have bn, and bn times this will multiply the whole of this, and then we have a and bn. So when they multiply, let's call all of these as, let's say, bn times a will still be a constant. Okay, bn times a will be a constant. Let's call that constant, let's say, small bn. Okay, then we'll have e to the k n pi over 2, sorry, n pi over L rather. then squared t, then sine of n pi over lx. Now, when you consider and you are saying that n should be equal to 1, 2, 3, and the rest. So when for every particular n you pick, you have a particular solution. So un, this one will be, let's say un of xt will be because it will be changing. For n equals 1, you have b1 e to the power whatever, put them there and you have a solution. When n is 2, you have that. But when you have plenty solutions for a particular question, then their sum, okay, should also be the solution to that particular problem. Okay, so here, since we are saying that we have plenty of them, we can also sum all of them, un of xt, then we sum everything, n equals 1 to infinity bn e to the k into n pi over l squared n times t, then sine of n pi over lx. Now this is the solution to the heat equation. Okay, and now what we are coming to do is to find our bn. Remember, in the heat equation, it was given, let me go and show it to you. It was given that the initial condition here is saying that u of x comma 0 is equal to f of x. So we'll need that. Okay, u of x comma 0 is what you are going to need. Okay, let me see, let me just see. Yes, so where is our u? Okay, our u of n is given by this. So we said that for the initial condition, u of x comma 0 is equal to f of x, meaning that our f of x will then be equal to, wherever I see t in this un of x, I'll put 0 there. When I put 0, is here, and that will give me e to the power 0, and that is 1. So I'll get summation n equals 1 to infinity bn, okay, sine of n pi over lx. Now I realize that this is actually the Fourier sine series of a function f of x. Okay, but this f of x is given as a condition, remember, so that will be given to you in a question. So since this looks like Fourier sine series, let's go and then with a constant bn. Okay, let's go and find the bn. In the Fourier sine series, given your f of x, we said bn is actually equal to, remember, the how do I call the range for x here is 0 less than or equal to x less than or equal to l. So we'll use the half range Fourier sine series formula, and that is 2 over l integral 0 to l f of x sine of n pi over lx, then dx. So you solve this for your bn, then you come here and put your bn here, and that will be your final solution. Okay, I hope this is well. So all that you need to do is make sure that your wave or your heat equation looks like this: ut equals some k, know your k very well. Okay, then uxx subjected to the conditions given. Conditions like u of 0 comma t equals 0, u of l comma t equals 0, and u of x comma 0 equals some f of x. And that if you solve them, if you have a question and it has all these conditions, the solution will look like this. I will advise that you always try to, if you have time, when you have questions, you always try to go through them yourself and get these solutions. But then if you can also know this, that the solution to the heat equation that looks like this, okay, that looks like this, is given by what we have here. Okay, with your bn as a Fourier sine series coefficient, and that is this one. Now let's apply this to an example and then we'll be done. Okay, solve this heat equation, and then this is the same as ut equals kuxx, because the del u, the squared u del s squared, right? Now we know that, look at here, you look at this side and realize that your L is still your L, okay, because it's L comma 0 comma t, sorry, and so your L is still your L. But your f of x here is the initial condition formula, and that is this one, u of x comma t. Okay, that will be your f of x. So here f of x is actually equal to 20. But we know that Fourier series that looks like this, or heat equation that looks like this, has a solution of un of xt being equal to summation n equals 1 to infinity bn, then e to the power, I said if it looks like this, okay, k into n pi over l squared and t sine of n pi over l then x. So let's say if k was something like, let's say 2, then you have to put 2 here. Okay, and let's say if l was given as, let's say 5, then you have to put 5 here and put 5 here as well. I hope you understand. But lucky enough, in this question, it was given as just L, and the f of s was the only thing that changed to 20. This means that your Bn is equal to, we said, is using the half range Fourier sine series, and that is 0 to L f of x, okay, sine of n pi over L x dx. And now our L is our L, so we have 2 over L integral 0 to L, but our f of s is 20, okay, sine of n pi over L x dx. Now if you integrate this, okay, I would surely not do this, okay, so when I put the 20 out, I have 40 over L, okay. And when you integrate this and put your limit in, I would urge you to kindly go through this. I'm begging you, okay, just go through them, and I know you'll be able to do that. When you integrate, you get minus L over n pi cos of n pi over L x from 0 to L, okay. So when you set your limit in, you insert L first, and you have minus L over n pi cos of n pi, okay. Then minus, when you set 0 in, already you have a minus L over n pi in front, so you get minus, and that will be L plus L over n pi into cos of 0, and that is 1. So all you get here is your Bn will be equal to 40 over L into L over n pi minus L over n pi cos of n pi. Actually, when you put the higher upper limit in, you get the minus this, then minus this one, that will be plus, okay. So I just interchanged it. I want you to go through the steps by yourself, or if you want, I can still go through them with you. Okay, so here, look at here, when you put the L in, here will be minus L over n pi, okay, then cos of n pi, because when you put x equals L, it will cancel the L here, then minus, okay, already have minus L over n pi in front again, then you put a 0 in, that will equal 0, so that will be times 1, so that will be it. So the minus will just go, and here it will be plus, okay. So this whole thing plus this, I can write it that this whole thing minus the other one, because there's a negative in front, and that's what we have here. But note that we said cos of n pi, or let's say we factor L over n pi out, so we have 40 over L, then you factor L over n pi out, then you have 1 minus cos of n pi, okay, and this will take this out, and that we have 40 over n pi into 1 minus cos of n pi is minus 1 to the power n, okay. So you put this there, and then your solution is, this is our Bn, right? So we are saying that our solution looks like this. Let me go back and this is our solution, right? This is it. Let me rewrite it again. The solution is un of xt, or u of xt, is equal to summation n equals 1 to infinity, okay, then bn e to the power k n pi over l squared, then sine of n pi over l x. So depending on the l given, but here our l was still l. So this means we have our solution to be 1 to infinity. Now bn is giving us 40 1 minus negative 1 to the power n all over n pi. Then we have sine of, okay, let's start writing the sine first, n pi over l x, then e to the power k n pi over l squared, then t. And this is our solution. Okay, I hope you understand. So this is very, very simple if you understand how to use the method of separation, how to find the eigenvalues and eigenfunctions. So here we used eigenvalues, eigenfunctions, and we've also used Fourier series as well. That is why I first of all did videos on eigenvalues and eigenfunctions and then Fourier series. Okay, so kindly go through them by yourself. You can sit and do it by yourself, and I hope you'll be able to do and answer all questions under the heat equation as well. Okay, so in our next discussion, we'll take the Laplace equation and also go through the derivation of the solution. Okay, so that we'll be able to solve them each and every day when we meet them. Okay, thank you, and don't forget to subscribe to my channel if you have not subscribed. See you next time.